When working with a distribution, it's often helpful to find the percent of data that falls within a span of values. And we'll use this idea of the percent of a distribution that falls within a span of values later in inferential statistics. Starting the foundation for this, we want to look at different types of distributions and then also what percent of data of that distribution will fall within a specific intervals. And the beginning of this process is with something called Chebyshev's inequality. Now, Chebyshev's inequality is something that works for any distribution, no matter how skewed it is. So it gives us kind of a ballpark figure, but it's really kind of your worst case scenario. It's like a minimum percent that you would expect of your distribution to fall within an interval. And then if we know more about the shape of a distribution, and later on if it has some specific types of shapes that we can depend on, then we actually get a much better feel for the percent of data that we expect to fall within an interval of data value. So here, let's just focus on Chebyshev's theorem to get started. So for Chebyshev's inequality, it says for any data set. So this is no matter how skewed it is. So again, it gives us a low ball figure for the percent of data that we would expect. Or distribution at least 1 minus 1 over k squared, that number times 100% of the distribution lies in the interval of mu minus k sigma to mu plus k sigma for k greater than 1. Now, a couple of things here is that statistics is laden with vocabulary and symbolism that you probably don't have in your normal vocabulary, and it's one of the things that you need to do from the very beginning of working with statistics is to really practice to get comfortable with the vocabulary and really practice to get comfortable with the symbols that are used for certain aspects of it. So here, mu is the Greek letter that stands for the population mean. So here we're talking about having the population mean of whatever that distribution is. And notice these both start with mu, and for this low end it's minus k sigma, and for the high end it's plus k sigma. So you're starting with your population mean for that distribution, and you're subtracting k times sigma to get a low number of your interval, and you're adding k times sigma to get a high number for your interval. So that's how we get a span of data values for the output of this idea. Now sigma next. This small k sigma stands for your population standard deviation. So remember, that is like your average distance the numbers of the distribution are away from their mean. And then k, well, this k is the k value that was from this calculation that we need to do to get our minimum percent of the distribution falling in this interval. So that's your number of standard deviations away from your mean. That's what your k is. Now, when we're looking at it, k has to be bigger than 1, because if k were 1, 1 squared is 1, 1 divided by 1 is 1, and 1 minus 1 is 0. So at least 0% of your data values in a specific interval actually doesn't help us at all. So that's why we need to have something where k is greater than 1. Now, Chebyshev's inequality could also be applied to sample data distribution. And if we apply it to sample data information, then remember the sample mean is x bar by symbols. So that would be x bar minus, and then k. And then for sample standard deviation, the symbol is s. So this will be x bar minus ks to x bar plus ks for our interval if we're looking at the sample information. Now, if these symbols are things that you haven't gotten used to, or you still are wanting to work on them, I have a video that's on symbols commonly used in statistics, And I'll put a link to it in the description of this video so that you can go back and look at that and just have that to kind of keep reinforcing the symbols and what they mean in statistics. Now, here's an example of a first part of way we can look at Chebyshev. So using Chebyshev's inequality, find the minimum percent of data that lies first in mu minus 3 sigma to mu plus 3 sigma. So here, when I look at comparing it to the interval part, they're giving me an interval and they're wanting me to find the minimum percent. So what I need to do is I need to compare this with the symbols for the interval and find out what the k value is so that I can plug it through this formula for Chebyshev's inequality and find my minimum percent. Well, when I look and just compare them, it's mu minus k sigma, and here's 3 sigma, to mu plus k sigma, mu plus 3 sigma. So k is this coefficient in front of your standard deviation. So k in this case is 3. So since k is 3, I'm going to just put it right up in this formula. So I have 1 minus 1 over 3 squared times 100%. Well, 3 squared is 9, so I have 1 subtract 1/9. Well, 1 subtract 1/9 is 8/9. When you take 8/9 and you divide that out, it's 0.888888. And when you multiply that by 100, it moves the decimal point over 2 places. So you get 88.8888%. So we'll go ahead and round that to 88.9%. Now, if you're doing this for some sort of online homework system or for a homework assignment for a class that you're taking, or if you're looking at how you want to report it, just look at what it signifies for what your approximation should be to leave it in the correct value. So some might want you to leave it as 89%, others might want you to leave it as 88.9%. Just look and see what their approximation requirements are. Let's go to part B. So here, using Chebyshev's inequality, find the minimum percent. So find this minimum percent of data that lies within. So here again, I have mu minus 2.5 sigma to mu plus 2.5 sigma. So this coefficient in front of sigma is your k. So here k is 2.5. So then I have 1 minus 1 over 2.5 squared times 100%. So 2.5 squared is 6.25. 1 divided by 6.25 is 0.16. And so when I take 1 and subtract 0.16, I get 0.84. Now 0.84 times 100 would turn that into 84. So then this would be 84%. Okay, now the third part here. Within 2 standard deviations of the mean. Well, within 2 standard deviations of the mean, think about when you use that idea of within in just normal vocabulary. Like if you say, I'm going to be at your house at 2 o'clock within 5 minutes. Well, then you're saying that you're going to be there either somewhere in the span from 1:55 to 2:05. So when you say within 5 minutes, that means you're going to take away 5 minutes or add 5 minutes to make your interval. So when it says within 2 standard deviations of the mean, they're really just giving you a written way of meaning the same thing as your mu minus 2 sigma to mu plus 2 sigma. Just another way of communicating that idea to you. So here our k is 2. So we have our 1 minus 1 over 2 squared times 100%. So 2 squared is 4, 1 over 4 is 1/4. 1 subtract 1/4 is 3/4. When I take 3/4 and change that to decimal, that's 0.75. And then 0.75 times 100 is Now let's look at some other types of questions they might ask us when we're doing Chebyshev's theorem. What we're going to do next is look at some additional ideas that are associated with Chebyshev's inequality. So I've just given a brief reminder of Chebyshev's inequality, and our first part says find K for at least 75% of the distribution, and then for B at least 80% of the distribution. So if you remember the one that we just did a few minutes ago, they gave us the interval in which we could figure out what the K was, and then they wanted us to find the minimum percent from giving us that interval. This time, they're giving us the minimum percent of the distribution that falls within the interval, and then we want to find what the K is. We're not supposed to go all the way and get the interval, we're just supposed to find the K value for this first part of the process. So we've got the percent, we've got this part, and we're just trying to find the K. So for this particular couple questions, we're not actually dealing with the interval itself yet. Okay, so at least 75%. Well, there's a couple of them that you'll want to remember because it just would be quicker than having to solve this around each time. And that is that when K is 2, 2 squared is 4, that's 1/4. 1 subtract 1/4 is 3/4. 3/4 changed to decimal is 0.75. And then 0.75 times 100% is 75%. And also, one of the other ones we did earlier in the video was when K is 3. So for K is 3, remember we got our 88.9%. So it's just really handy with Chebyshev's inequality to remember that if it's at least 75%, your K is 2. If K is 2 for Chebyshev's inequality, then your percent is at least 75%. And then if your percent is 88.9%, your K is 3, and if you have a K of 3, then your minimum percent is 88.9%. So those are just handy to have in your mind. So as soon as I see this at least 75%, that's one of them that I've done so many times that I know that that means the K is 2. But let's say you forgot it. How would you do that? Well, this 75 is the percent. And if I change that to decimal form, if I go back to the, not the percent form, but the decimal form, that's what this first part of the expression would have to equal. So that would mean my 1 minus 1 over K squared would have to be 0.75. Now to do this, a quicker way of working with it would be to subtract the 0.75 from both sides and add the 1 over K squared to both sides. So then I'll have 1 minus 0.75 is equal to 1 over K squared. And that just helps me get it rearranged a little bit quicker. So again, I just subtracted the 0.75 from both sides of the equal sign and added the 1 over K squared to both sides of the equal sign. Well, 1 minus 0.75 is 0.25. That's equal 1 over K squared. Now, multiply both sides by K squared. Remember, K squared can't be 0. It has to be actually greater than 1. So you can multiply both sides by K squared. So I get 0.25 K squared is equal to 1. Divide by 0.25. K squared is equal to 1 divided by 0.25. Now, if you key that through, 1 divided by 0.25 is 4. So 0.25 is a quarter. 1 divided by 1/4, remember if you're dividing by a fraction, you flip and multiply. So 1 divided by 1/4 is 4. So I get K squared is equal to 4. And when I take the square root of both sides to solve for K, I'm not going to use a plus or minus because K has to be greater than 1. So this K is equal to the square root of 4, which is 2. So K is equal to 2. All right, now using that thought process, let's do the next one, at least 80%. So again, I'm going to have 1 minus 1 over k squared is equal to 0.80. Subtract the 0.80 from both sides and add the 1 over k squared to both sides. So that's 1 minus 0.80 is equal to 1 over k squared. Well, 1 minus 0.8 is 0.2 is equal to 1 over k squared. What we saw over here we're going to do, so we're going to multiply both sides by k squared, and we get 0.2 k squared is equal to 1. Divide both sides by 0.2. K squared is equal to 1 over 0.2. And then when you go through and you divide that and take the square root, you get k is approximately equal to 2.24. So our k for at least 80% is k is equal to 2.24 approximately. Now that makes sense. Our k equal 2 is 75%. Our k equal 3 is 88.9%. So I would expect the k that gives me 80% to be somewhere between 2 and 3. And we got our 2.24. All right, so those are those two. Now, how about this last one? It says for distribution with x bar equaling 32. Well, x bar, remember, that's your sample mean. So your sample mean is what at in the interval where the population mean is for when we did the population work. So our sample mean is 32, and our sample standard deviation is about 2.47. So remember the sample standard deviation, that's playing the role of what the population standard deviation did when we were doing our work there. Now I just need to have my k in order to make my interval. And it says find the interval for which at least 88.9% of the distribution lies. Well, 88.9%, if I didn't remember that that's one of the ones that had gotten from doing our work when we were first working through it, that came from k equal 3, I would just do the work we just did on these two to find out what the k is. But we already did that and reminded ourselves of it, so that means that k is equal to 3. So I have my interval of x bar minus ks to x bar plus ks. X bar is 32, and subtract our k is 3 times our s value is 2.47. 2x bar is 32, and it's plus k is 3, and our s again is 2.47. Now when you get to the point that you have it here, remember your order of operations if you're going to key it in separately. If you just key it in and don't put too many parentheses around it, your calculator is going to understand the order of operations and give you the right value. But if you're going to key it in separately, remember, it's please excuse my dear Aunt Sally, so what's in parentheses first, then exponents if you have them, and then multiplication, division as they occur from left to right, and then addition, subtraction as they occur from left to right. So we need to carry out these multiplications before we do the subtraction and the addition. So when you go through and key the whole thing through, your low number is going to be 24.59 and then the upper number will be 39.41. So that's your interval for which at least 88.9% of this sample distribution lies. In this next question, we're going to look at pretty much a more broader type question and how things actually might be asked when we're taking it as its whole global reach. So here, Chebyshev's inequality again Any distribution at least 1 minus 1 over k squared times 100% of the distribution lies in mu minus k sigma to mu plus k sigma, that interval. And k has to be greater than 1. Now, here they're giving us data. So they didn't give us the mean and the standard deviation. They're actually giving us the distribution of the numbers. So when we look at this data, the very first thing it's asking us to do is to find the sample mean and find the sample standard deviation. Now, if you're working with a statistical program or you're working with a graphing calculator, you can find the mean and the standard deviation from the program that has been embedded within either the statistical computer program or your graphing calculator. So with a graphing calculator, specifically the TI-83 or the TI-84, you're going to go Stat, Edit, and in Edit, once you push the Stat button and then choose the option of Edit, you're going to get lists, L1, L2, L3, etc. You're going to put all these numbers in L1. So you just push the 46 and push enter and it'll pop down, and you'll push the 52 and push enter and it'll pop down, 45 push enter, 97 push enter, etc. to get all your data in. And we have 2, 4, 6, 8, 10, 12 pieces of data. So when you get to that last one and it's sitting on that last number, it should say that your n is equal to 12, or you have 12 pieces of data in there. Now once you do that, you're going to push the Stat button again. And this time you're going to cursor to where it says Calc. And right under the Calc menu, the very first one is 1 bar Stat. And you're going to push enter on that. And if you put your stuff in L1, it defaults to looking at L1 for the data. And so you can just push enter again. If you have a menu-driven graphing calculator, which most of the newer ones are, it's going to ask you that the list was L1. If it says frequency, don't put anything after that because we don't have any more frequent numbers on like a frequency distribution table that we put in. And then get your calculated values. And X bar is at the top of the screen. And X bar is going to be 47.42. And then your S is going to be approximately 18.55. Approximately 47.42, and S is approximately 18.55. So getting those values. Now it didn't actually have to ask me to do that to start with. I would just have to remember that I need those values to do the interval if it started right at this first question. But it's kind of nice that it did to get us going in the thought process. Now, centered about the mean, for which you would expect at least 75% of the data. So it wants me to find this interval. Mu minus k sigma, mu plus k sigma. So it's the interval centered about the mean. And for which at least 75% of the data. Well, the information that we just did, if they're asking me at least 75% of the data for Chebyshev, that's telling me k is 2. That's one of those that we wanted to remember. So our interval is X bar minus ks to X bar plus ks. X bar is the 47.42, and it's minus 2 times the 18.55. To X bar, so 47.42 plus the 2 times 18.55. Now when we go through and we calculate that through, we'll get our interval is 10.32 to 84.52. So that's our interval centered about the mean that we would expect at least 75% of the data for Chebyshev's. Now the last part, this I kind of abbreviated the directions, but I'll just talk through it. So we want to count the number of data values that actually fall in that interval. So when I look at this interval from 10.32 to 84.52, 46 is a number somewhere between 10.32 and 84.52. 52 is a number somewhere between 10.32 and 84.52. And in fact, when I scan through it, the only one that's not in that interval is 97. Now I had 12 numbers altogether. There was only one that isn't in the interval, so there are 11 numbers that are. So there are 11 data values that fall in this interval from 10.32 to 84.52. Now, what percent of the data values is that? Well, it's 11 out of 12. And 11 divided by 12 turned into percent form is about 91.7%. So for our data set, about 91.7% of the data values actually fell in this interval. Now, does that agree with Chebyshev's inequality? It does, because Chebyshev's inequality says for which we would expect at least 75%. And 91.7% is at least 75%. At least 75% means 75% or more. So, yes, it does agree with Chebyshev's inequality. So hopefully the examples that we did gives you a little bit more understanding of Chebyshev's inequality and the ideas that they're asking for when they ask you different questions about specific components of Chebyshev's inequality, or actually asking you to work a problem on a data set from start to finish.